In this video I will code a basic working example of pulse width modulation on the stm32f4 in Rust. So I previously did a basic setup tutorial for Rust with Cargo, specifically aimed at microcontrollers or the stm32f4, and in these videos that I did, I coded a simple Hello World application. Now here I want to take this a step further and do something at least a little bit more complex. So if you haven't watched these basic setup videos and you need a couple of ideas there maybe, you're more than welcome to watch those and come back here after that. And otherwise, I'd say let's get started with this.
So without further ado, let's jump right into coding, and I'm gonna just open this source main.rs with my favorite editor, and in this section of the video I'm just going to add the groundwork, or let's say the framework that we need for doing embedded Rust. So the first thing that we're gonna need is a macro, and this is gonna be no main. This here, right here, this just says we don't have a standard main interface, so no standard main interface. This includes things like command line arguments that are parsed and so on. So you're just gonna add this for embedded, and we're gonna come back to it in a moment. The next is this no standard, so no standard crate is going to be loaded. Then, continuing, of course there's a main function, and this main function here returns this exclamation mark. Now this exclamation mark, it just says there is going to be no value that is returned, so this function never returns. So I'm going to say exclamation mark equals this function never returns. So next we have to specify an entry point for our application because of this no main. So we're going to do that here, and we're going to take this from this Cortex MRT, and we're going to say entry here. And then of course we're also going to use this stm32f4 crate, and from that we're gonna import this 401 processor. So now I think we're ready to get some peripherals, and we can do that with peripherals equals stm32f401, and then here we can say peripherals and then take. And then here we're just going to do an unwrap. Now from the documentation of the crate we can find out that this take from this peripherals, where peripherals is going to be a struct, returns all of the peripherals, but it returns them as an option. And this has the following form: option self. So we have to unwrap this option. That's why this unwrap is here. And if you are unsure about this, you can always just look up the documentation of the crate, and here you can see this peripherals, and then if you just come down you can see all of the peripherals you have in there, and then also this take with the option. Now for the pulse width modulation, we're going to need a couple of things. First of all, we need RCC. Now, RCC is the register that is used for clock control, or just is comprised of everything you need for clock control. And here you can see all of the registers that are in here. Now, if we just check this memory map, we can see that things like the GPIOs or the CRC are connected to the AHB1 bus. That means in here we have to use the AHB1 enable registers for the GPIOs, for example. But other peripherals, for example this timer 3, are connected to APB1. That means in here we have to look up the APB1 enable register. As you can see here, there is, for example, the enable in here for timer 3. So just keep that in mind. So next we're going to need a GPIO pin, and I'm just going to select GPIO A here, and again I'm going to take this peripherals. Note that this ampersand here marks a reference, and from here I'm going to take GPIO A, and I also want a timer, so I'm just going to do the same thing, and from the peripherals I'm just going to get timer 3. Of course you can also use a different timer if you want, but I just selected timer 3 for this. So for the clock gating, I am going to activate in the AHB1 enable register with this write the GPIO enable. So take the GPIO enable register and say set bit. Things like this you can also find in the crate documentation, as I showed you right here. If you just go back to the stm32f4, you can see here there's the GPIO-A, and then eventually you will see all of the registers, and for RCC there's of course also something like this, and here's this AHB1 enable register, and you can see here there are these structs, and there is this GPIO-A enable, and this is just going to be a proxy field, but here you can find the set bit function. Now this can also be done in a similar fashion for the timer, but the timer is connected to AHB1. So here of course we also need another field, then up top, and then we can activate the clock gate for timer 3. So to go over this a little bit more quickly, I copied in some code, and this is from line 20 to 29, and here I'm utilizing GPIO A6. So first of all I set the pull up pull down register to floating, the push pull output type in the output type register, as you can see here, and the alternate function mode in the mode register. Now these functions here, like write and modify, they use a closure, which you can see here, and write only does write, modify can also read, but I'm not using this read, so I have an underscore here. Now the next thing that is important is actually this AFRL, which we will look at in a little bit more detail. Good. Now about these AFRL and AFRH registers. I'm here in the reference manual and in chapter 8 general purpose IOs. Now here you can get an explanation of the alternate function mode or the alternate function configuration, which we are going to need for the PWM configuration. Now from this you can already get some information, but the question is still, what alternate function number do we have to select, and how do we get this alternate function to the pin that we're using? And down here under GPIO registers we can find this AFRL and this AFRH. Now let's have a look. This is the alternate function low register, and it depends on the pin you're using. So here it says alternate function selection for port X, bit Y, and Y is 0 to 7. So the port would be for GPIO A, for example, it would be port A, or port B for GPIO B. And in the AFRL, so in the low alternate function register, you can do the configuration for pin 0 to pin 7. Now in the high register, we can do the configuration for pin 8, as you can see here, to 15. And that's what this is. Now we're using pin 6, so that means we would be here in AFRL 6. The next thing that we have to find out then is which of these alternate function numbers, AF0 through AF15, we have to use for the specific pin and for the PWM configuration. And if we jump back to the code, you can see I'm using AFRL 6. And I'm going to modify this to alternate function 2. Now, here to find out what the correct alternate function is, you need the datasheet of the controller you're using, at least for the STM. Now, here I have the datasheet, and under chapter 4 pin outs, you can find this table alternate functions. And here you can see PA6, and PA6, the alternate function for timer 3 channel 1, which is what I want, is listed under alternate function 2. That's where I got this from. So remember, always, you have to always discriminate between the reference manual and the datasheet. So now to the PWM mode. Here you can see that in this chapter 13, for timer 3, there is a description of the pulse width modulation mode. Now, in this tutorial, I'm just going to use the description here to add the code that we need to get PWM working. So here I have now added the necessary code, and this is just the description from the manual about PWM, so I am not going to go into this in detail. One thing that I want to mention here is do not forget to enable this update generation, as the manual explicitly states that this is needed at the first start, and of course start the PWM by setting this enable register in, or this enable bit in the CR1 register. Now for the more interesting part. One thing that we're going to need is a timer frequency, and the other thing is a duty cycle. Now how do you set that? Well, the ARR register in the timer is actually used to set the frequency. This frequency depends on the source clock, and the duty cycle is set in the CCR1 register. So here we are setting multiple bits in a register, and Rust doesn't like that. It's considered as unsafe. So the API of the stm32f4 crate tells us that it's unsafe, and we have to make that known to the Rust compiler. And that's why there is this unsafe that we can use and just wrap these functions in there. So I'm going to show you this. As we already know, we have this write with a closure, and here we set multiple bits. And when we compile this later, I will show you that without this unsafe, it won't actually compile. So here is the frequency, and then also this timer CCR1 is going to contain the duty cycle, which I will set to 0 here, and we will see why later. So we have to jump up to the beginning of the file real quick because I forgot something, and that is this panic handler right here. So this has to be imported as an extern crate. If we don't have this, we actually can compile. And the thing is, this just makes the microcontroller go into a halt state when something panics in our code. Okay, now so here I added a mutable variable duty cycle, which is of type U32, and set it to 0. Because the duty cycle was set to 0 here, my plan is to change this duty cycle continuously in the main loop. So for that, as we have it up here, we are going to need some unsafe Rust. Okay, now let's code that in. So we're going to say unsafe again, and then we can take this duty cycle from here, just add it, and then instead of excuse me, instead of going for this 0, 0, we can just put in duty cycle. And then of course down here, outside of the unsafe, we're gonna increment this, and I'm just going to increment it by 255, and then modulo this with the value that we put in for the frequency. So this is pretty much it. All we need now is some kind of a delay function, so this doesn't go too fast, and I'm just going to add this in here. Now here I added the delay function. It's very simple. Just for I, this underscore just tells the compiler we're not going to use I, so we don't care about this variable here, and we're going to have it count from 0 to 999. And that should be everything that we need. And now we can go on to compile this. Alright, let's look at this code and what happens when we comment this unsafe. You can see here, when you do a cargo build, I did this with without commenting the unsafe. It works fine. Now let's build again, and you can see here it's a call to an unsafe function, so it won't compile. So we need this unsafe function block. Now you can always take these explanations from the Rust compiler and maybe get some help there. So let's just paste this in, and you can see here what is deemed unsafe. So here, in our case, this is actually going to be the reason why this won't compile, because the function is marked unsafe. Now, if you do a little bit of digging into this API, you can see that the bits function here is explicitly marked as unsafe, and that's why it won't compile. And that is the reason we have to use this unsafe block. And there are more reasons, as it says here, for instance, dereferencing a raw pointer. Now, I put in the unsafe block again, and then when we do cargo build, you can see it builds just fine. Okay, now let's run this on the microcontroller. First we need an OpenOCD connection, and as you can see, connected to the microcontroller without any problem. And now here I'm going to do a cargo run. Now GDB starts up and we have to connect to the remote target. This is done here, and I already have a program running on here, so just ignore these messages, and I'm going to say load the program. It's loaded to the microcontroller now. It went pretty fast actually, that's nice. And then I'm gonna set a breakpoint at main. And just say continue here. So now I'm at entry that we coded, and just to show you this, I'm gonna say layout source here, and this is where we are. So if I run this now, I should see some effect of the pulse width modulation. I connected an LED to pin A6, and through this changing of the duty cycle with that little delay, the LED should go from off and then gradually become brighter and brighter and brighter until the duty cycle is 100%, and then it will just go back to off again. So here we can just type continue, and I will show you in a minute that this actually works. So I hooked up my webcam, and the quality is horrible, but nonetheless you can see this LED slowly going from off to getting brighter and brighter and brighter and going back to off again. So from this little demonstration with the LED, it looks like the PWM is working, but nevertheless I'm going to show you the output of the scope so you can be sure that everything's okay. Okay, so here's a quick video of the scope output, and you can see here the PWM works just fine. It starts at 0 and then the duty cycle is changed until it reaches 100%, and then it just drops back down to 0 and starts again. So now you can see the PWM works fine, and I gave you the code, everything you need to know if you want to continue working on this, add more features, try out different PWM modes, change the frequency and so on, can be found in the reference manual where I pointed you to. And with that being said, I think I will sign off now. So thank you for watching and goodbye.